Hello and welcome everybody to the world of conditional statements. These are going to be our notes on Unit 2, Chapter 2. So what is a conditional statement? A conditional statement is a statement that can be written in the form if P, then Q, right? So let me get my highlighter here. If P, then Q. The hypothesis is what we call the P part of this statement, and the Q would be our conclusion. Most often, these are conjectures that we will use as an if-then statement, right? Using the if and then structure, it's easy to identify which is the hypothesis, that'll come after if, and which is the conclusion, that'll come after then. So let's think about some examples here. So here we have an if-then statement. So we know that the first part after the if is going to be our hypothesis. Today is Thanksgiving. So that would be the hypothesis. Today is Thanksgiving. And then the conclusion of this if and then statement would be coming after the then part. Today must be or is Thursday. So when we break these down, if and then are extremely valuable, right? So at this point, we're not super concerned about whether or not these are true. We'll talk about that in a little bit. But what we're concerned about is identifying the pieces of these conditional statements. If today is Thanksgiving today, then today is Thursday. If leads us to the hypothesis, then brings us to the conclusion. Let's look at choice B here. Not choice B, example B, excuse me. A number is a rational if it is an integer. So this one is written a little bit out of order, but that if word is super helpful for us. If a number is an integer, so let's even get rid of the if. A number is an integer, then the number is rational. Right, so that word if, it can come at the beginning of the sentence like it did in example A, but it's not guaranteed. It's not always going to happen in the same order, so we just have to make sense of what's going on. Use those indicator words if and then when they're available. Let's look at example C here. In example C, the statement is made, a number is divisible by 3 if, hey, there's our word, if it is divisible by 6. So that if tells us that we have a number is divisible by 6. A number is divisible by 6. And then our conclusion, it doesn't come with a then statement here, but our conclusion is going to be the first half of this statement. A number is divisible by 3. So there's some different ways that you may see these type of statements written, right? We are basically using, right, P leads to Q. But the other ways you may see this, either in your textbook or other places, right? You can see these here. If P, then Q. That's one way we can see it. If P, comma Q, right? All of these saying the same thing. Q if P, P implies Q, and then finally P only if Q. So we will mostly use this arrow notation, but we're going to use conditional statements in a variety of ways. We're going to move on to the next page of our notes. So here we can see that many sentences without those indicator words if and then can be written as conditionals. What we need to do is we need to figure out which part of the statement depends on the other. All right, so we're gonna look at a few examples here to see if we can make sense of them. I am going to work through each of these. If you want to pause and try them on your own at any point, that's the advantage of being on video here. So here in statement A, they tell us an obtuse triangle has exactly one obtuse angle. So what we need to do is determine our conditional statement. So what we know is that if a triangle were not obtuse, it would have no obtuse angles. So what we would say, our if statement here is if a triangle is obtuse, then it has exactly one obtuse angle. It has to go in that order because the one obtuse angle would make this, exactly one obtuse angle is our conclusion, because we need to have an obtuse triangle in order to have any obtuse angles at all. Let's look at another one. Here we have this nested Venn diagram. That was an unexpected joke there because we're talking about birds and blue jays, and we have a nested Venn diagram here. And there's a note just below. The inner oval represents the hypothesis, the outer oval the conclusion. So what we're going to say with our hypothesis, if an animal is a blue jay, then it's a bird. Blue jays are all birds, right? That depends on us being in the realm of birds, that the specific blue jay, this specific bird is a blue jay. So if I know it's a blue jay, I also know it's a bird. Finally, we have another written out example here. Two angles that are complementary are acute. So the way we would write this, well, we know that if I have two angles that are complementary, they must be acute. The acute angles don't create complementary angles necessarily, but if I have complementary angles, I must have acute angles. So the acuteness depends on the complementary nature of these angles. So we would say if two angles are complementary, then they are acute. So there's a lot of ideas here, right? This idea of dependence, right? One leads to the other. And I think that's the most valuable way to kind of frame this as we look towards what we're calling a truth statement, a truth value. All right, so let's talk about that. A conditional statement has a truth value of either true or false, and this is a strange idea. It is false only when the hypothesis is true and the conclusion is false. So what we're really looking for is, does P lead to Q? And even if, the only case where we can say that this is true or not true, when it's not true, when it's false, is if we know P is true and we have a counterexample where the hypothesis is true, but the conclusion is false, right? The truth statement worries much more about whether P leads to Q rather than are both P and Q true. So let's look at some examples here. So here's our statement. The hypothesis is this month is August. The conclusion next month is September. There's really no other way to come up with this. I think that because it's a socially generated calendar, we know the order of our month is fixed. August always leads to September. There's no way to make this statement false. If this month is August, the next month is September, there's no counterexamples we can create. Let's look at example B. If two angles are acute, then they are congruent. Remember, congruent is one of those words we say is identical. They are equivalent. So if two angles are acute, so we're only thinking of acute angles, then they are congruent. Is it possible to come up with two acute angles that are not congruent? Well, sure. We can use a 30-degree angle and we could use a 31-degree angle. This would make our statement false because we had two acute angles, but they were not congruent. Because our hypothesis didn't lead to the same conclusion, we can say that the whole statement would be false. We can turn to the next page here. We're getting close to wrapping things up. This is a strange idea, all right? And I'm just going to put an asterisk here. This is something to just kind of sit and think about. If the hypothesis is false, the conditional statement is true regardless of the truth value of the conclusion. This is a strange idea, I agree. So what we say, and here's how I can wrap my head around it. We're trying to see, does P lead to Q? Well, if P isn't true, then we can't really say anything about the relationship of P and Q. If the conditions for P have not been met, there's no way of knowing whether or not P leads to Q. So it's really there's no way to perform this test. It must be true because we have no way of knowing. All right, so there's some other related conditionals here that we're going to talk about briefly and explore on the next page. These related conditionals, I'm going to try to get them all together in one spot here so you can see what we're talking about. So our first conditional, P leads to Q, we've talked about already. Nothing to add. If and then statement, if P, then Q. The converse takes the original statement and flips the order, right? We flip the direction of the if and then. So you can see here symbolically, instead of going P to Q, now we're going Q to P. The converse flips the order. The inverse, and this is tricky because those words seem very similar, but the inverse is a negation, all right? If not blank, then not whatever our then statement is, right? If not blank, then not, right? We negate both the hypothesis and the conclusion. And the way we show that is with this little squiggle line. We would read this as not P and not Q. And then finally, our contrapositive is basically the converse of the inverse, if that's not too confusing. The contrapositive, we flip the direction and negate both statements. So when we go from our conditional to our converse, we flip the order. And when we go from a conditional to an inverse, we negate both statements, not P and not Q. The contrapositive does both, flip the symbols and turns our positive statements into negative ones. We need some examples to make sense of this. So let's turn over to our last page here. So we have one example basically fully worked out, and we have this science fact that it's based on. Adult insects have 6 legs. No other animals have 6 legs. Our statement, our conditional statement is if an animal is an adult insect, then it has 6 legs. So here you can see we're going to mess around with this statement and move things a few different ways. What we're going to do along the way is determine the truth statement of each of these. The truth value of each of these statements. So the converse, we flip the order. If an animal has 6 legs, then it is an adult insect. We know that no other animals have 6 legs, so that one must be true. The inverse, we take our original and we negate both P and Q. If an animal is not an adult insect, then it does not have 6 legs. Well, that's also true, right? If we know that the only animals that have 6 legs are adult insects and it's not an adult insect, then it's not going to have 6 legs. Finally, we have the contrapositive. If an animal does not have 6 legs, then it is not an adult insect. And this is also true, right? This is not always going to be the case. All these statements can have different truth values. In this case, each of the 4 statements, the conditional, the converse, the inverse, and the contrapositive were all true. I'd like you guys to pause the video here and try this on your own. Obviously, I'm going to be here in a moment working these out and explaining my thought process, but this is where we're going to leave it. So now is a good time to pause and try to write the converse, inverse, and contrapositive of each of this statement. If an animal is a cat, then it has 4 paws. All right, with some movie magic there, now we have our statements. So the converse here, we flip the order. The original statement said if an animal is a cat, then it has 4 paws. We flip the order. If an animal has 4 paws, then it is a cat. I would say that's false, because I can think of an animal with 4 paws that's not a cat, and I would say that is a dog. For our inverse, this is the case where we negate both statements. We say if an animal is not a cat, then it does not have 4 paws. Well, again, that's going to be false. And again, we're going to use our trusty dog here to be our counterexample, right? If an animal isn't a cat, then it doesn't have 4 paws. That's just false. Because we can come up with an animal that's not a cat that does have 4 paws. The contrapositive here, if an animal does not have 4 paws, then it is not a cat. This is a true statement, right? All cats have 4 paws. Therefore, if an animal doesn't have 4 paws, then it is not a cat. Our last thing we're going to end up here is just this hint at the bottom of the page. Related conditional statements that have the same truth value are called logically equivalent. A conditional and its contrapositive are logically equivalent, as we saw in this past problem. We saw the contrapositive and the conditional both being true. And then the converse and inverse are both logically equivalent, and what we saw in our example is that they were both false. So they're very much related. The logical equivalence of a conditional and its contrapositive is known as the law of the contrapositive. And that's where we'll leave it. I appreciate your guys' help, your attention today. Thanks for your time.